of an impulse. No matter how narrow you make it, it becomes taller and taller, but the aggregate area is always 1. Okay, that is called an impulse. So what happens then is that this actually becomes an impulse. This would be just empty convolving with an impulse function. Okay, an impulse function. So but what is so special about the impulse function is such a narrow function. If I have any function multiplied by an impulse function and integrate, okay, this is such a narrow function. It is 0 everywhere, but at the origin it's not 0. Okay? And you can approximate this to a very good approximation as the value of this function at 0 times the integration of this impulse. You can think of it as a limiting case of this. It becomes so narrow that all the other points are not important except for the point where t is equal to 0. But what is the area under this impulse? 1. Okay, so this is f of 0. Okay, there's one property you know about impulse functions. Another property is that if you have the impulse function shifted and integrate, okay, so this impulse function is going to be infinity only at t equal to t0. So if you look at the integrand, where does it peak? Where does it go to infinity? It goes to infinity at t equals t0. Only the value of this function at t0 matters. So you can actually evaluate this function at t0 and then integrate the impulse again. And what is the area of this impulse, even if it's shifted? It's 1, okay, f of t0. So the impulse function has this property that when multiplied by any function, it just takes its value at that particular location. Okay? So from this derivative property, you can easily convert the convolution with a unit step function to a convolution with an impulse. Okay? With an impulse. So and this is the first precursor to it, what an impulse function is. I will not talk more about it at this point, but let me talk to you about the property of convolution. What is actually happening here? You have f of t, say f of t looks something like this. You have h of t, let's say that h of t looks something like this. Or maybe something like this, okay, to make it more interesting. Okay? So when you want to find y of t, you actually perform this integral f of t times h of t minus tau. You perform this integral, and what actually are you doing? If h of t looks something like this, as a function of tau, how does h of t minus tau look like? First, let me ask you, if h of t looks something like this, what does h of minus tau look like? It's just this flipped around, right? And then what about t minus tau? When tau equals t, the argument is 0. So the origin point gets shifted to the point where tau equals t. So it gets flipped around and looks something like this. This function looks something like this. So the second term looks something like that. The first term remains unchanged, it's just changed to a new argument. So you multiply this function together with that function. You can change this to tau if you want to. So what happens here is that you're actually multiplying this function with that function. You multiply them together, and you see that they're only non-zero over here. non-zero over this domain. Okay. And this is t equals tau, or tau equals t. Okay, this is tau. So you're actually flipping one of the function mirror image, multiply them together, and integrate the overlap area beneath them. That's what you're actually doing graphically when you do a convolution. Okay? And then when you change t, what happens to the second function? When you change t, the second function moves to the right. Okay? When you set t is equal to 0, it moves to the origin. Okay? When t is less than 0, what happens to this overlap integral? When t is less than 0, there's nothing. Okay, there's nothing between them. When you multiply them together, it is equal to 0. But when t starts to move to be larger than 0, there's an overlap integral. Okay? So you will see that the final response, I don't know how it looks like, but then it will look something like that. It might look something like that. Okay, just plotting the overlap integral. Okay, it will look something like that. When t is less than 0, there's no overlap between them. Okay, when t is larger than 0, you start to see an overlap integral, and then the overlap integral picks up, and then when t becomes very, very large, when this thing moves all the way to the right, then the overlap integral becomes very small again. So that is the kind of response that you get. Graphically, you think in your head as to what a convolution is doing for you. Okay? So, if you have two unit step functions and convolving with them together, what do you get? If you have one unit step function convolving with another unit step function, what do you get? You flip one around, you flip one of them around, mirror image, and then move them slowly across. When t is less than 0, there's no overlap between them. When t is larger than 0, you start to pick up an overlap. The overlap between them is always 1, because it's 1 times 1. Okay? So if you have ut convolving with ut, it gives you t ut. Can you see that? That the resultant function just goes up like that. Because you flip one around, when t is less than 0, there's no overlap, so it's 0. But as you increase t, the overlap integral starts to increase, and the area underneath increases linearly with respect to time. So you have this property. And then you have the property that I just stated before, which is that if you have ht convolving with delta t, anything multiplied by delta t when integrated always gives back itself. Okay, this just gives you h of t. Okay, this is one other property that you have, and then if you have this convolving with delta t minus t naught using the property of the delta function, this just gives you t minus t naught. Okay, and then if I have two rect functions convolving with another rect function, a rectangular function, what do I get? I flip one around and then start to move them across each other. Okay? If you have t larger than certain time, or less than certain time, there's no overlap. Say if this is A, this is B, you flip one around, there'll be no overlap. And so what happens is that as they overlap, you pick up an area. Okay? You pick up an area, and that you start to have an overlap when this is equal to minus A minus B. This is equal to A plus B. You can go through the pictorial diagram and flip them around and move them back, and then they would have an overlap integral until you have t equals to A minus B. And then as the overlap, you find the area underneath is very much like this. You pick up a linear area, you get a triangle. So convolution of a rectangular function with a rectangular function gives you a triangular function. Okay? What is the Fourier transform of a rect function? Is equal to